Okay, I'm just making sure that all the settings. All right. So I realized that from some of the juniors that Mr. Manahan hasn't been dealing with these concepts in depth. So I took the liberty to hand to just show you guys what you guys missed. So starting with position and coordinate system. So in order to define a specific point, we need to establish an origin. Now, as you can see here to the right, you have, of course, the coordinate system with three dots, red, black, and yellow, right? So the black dot is at the origin, or what we call 0, 0, right? So after we establish this origin, then we can identify the position as the distance from the origin and the direction away from the origin. So what does that mean? So we have these red and yellow dots, where the red dot is 3 units to the left, while the yellow dots is 2 units to the right. And what I said there, 3 units to the left, 2 units to the right, those are position terms, right? I am defining a position relative to this uh, other point, right? This origin that we established. And from there, we can actually create something called a vector, right? Vector is basically a quantity that is defined as a magnitude and a direction. What that means is there is an amount, the magnitude, and there is a specific direction that that amount is pointing at, right? So based on this conjecture, position therefore has to be a vector, right? Because what position has is a magnitude, which is how much units it is away from the origin, and the direction, what direction it is, specifying in relation to the origin. Right? And what we can do is, now that we understand that position is a vector, we can notate vectors as this a variable with this arrow as a hat. So with vectors, this is what it looks like. Established, we can move on to how to add vectors. Right? So this problem is asking us, how do you add vector D and vector E? Well, it's actually not. It's very simple. Pretty much all you have to do is, from the black arrows, you slide the tail of the arrow all the way to the tip of arrow D. Let me say that again. You take the tail of vector E, then you slide it all the way up to the tip of vector D. And what you formed is kind of this hypotenuse-like vector that stems from the tail of D and reaches to the tip of E, right? Or you can make a vector that spawns from this point right here, right? You see how that the vector E didn't actually move, it just stayed right there. And you can form the hypotenuse like, arrow from your origin, right? From this point right here, until you form a parallelogram. Now, a parallelogram, if it's been a while, it is basically a four-sided shape with two pairs of sides that are equal and parallel, right? So this vector E is the same magnitude as this imaginary line, and this vector D is the same as this imaginary line right here. Okay? Now, knowing that we can add vectors, subtracting vectors, it's actually the same concept. Now, the reason why that subtracting vectors, it doesn't really involve all that much, is that when you subtract something, it is the same as adding its opposite. So if I take the expression 3 minus 2 equals 1, right? Then it is the same to say 3 minus or 3 plus negative 2 is 1, right? So knowing that we can rewrite the expression, what we could do is, first of all, they asked us to do vector A minus vector B, right? So first, I draw vector A, okay? So kept that the same. Now, what we did here was we actually took the negative version of vector B. And because of this, we need to flip the arrow, right? You can see here that that's why I have the plus over negative, because we are switching the direction, because all the negative does is to basic that the negative just basically flip the vectors, right? They just put them in the opposite direction, right? And then of course we follow our head to tail, or we do the parallelogram, whatever you want. And then we form the triangle, right? So vector A plus the negative version of vector B, and then would equal to vector A minus vector B, right? And this vector A minus vector B stems from this vector A tail, right? Okay. Moving on to displacement. Now, displacement is basically the change in the object's position, right? So it's notated as the change in this little triangle thing of the position would equal to the final position minus the initial position. So back to our graph. If I were to ask you what is the displacement from the red dot to the yellow dot, it would be, well, we are going to the yellow dot, but we are starting at the red dot, right? So yellow dot is our final position, which is 2, minus our initial position, which is -3, would equal to -5, right? So from there, what we also know is that displacement is measured in meters. So again, going over that same idea of this 5 units. Now we can assign a unit, right? So from the red dot to the yellow dot, it is 5 meters apart, right? That's the displacement. Now I want to make this very clear. Displacement is the shortest path between two dots, right? Two position. Distance, on the other hand, is scalar. You can approach those two dots infinitely in however way that you want to approach it. I can approach this normally, like going across a straight line. I can approach it going around the black dot. I can approach it doing this weird squiggly motion and then approaching to yellow. Like, you can do all sorts of things, but in the end, distance basically describes the path that you're taking, or displacement describes the shortest path that you're going to take, right? Now, with displacement discussed, we actually move on to how to represent, motions, and that brings us to motions and particle diagrams. So you can see here that to the right, it actually shows us a 3D object moving, but it's represented in a one-dimensional model, right? So from here you have the motion diagrams, and here you have the particle diagrams. So the particle diagram is just basically a representation of the motion diagram, except it's more, it's more simpler because the person who's drawn this actually just simplified the cars to be just this one dot, right? This one single object to make it easier to analyze the motion. And you can see here that from between these dots, time has passed, right? The same time has passed. So what I mean by that is from dot 0 to dot 1, 1 second has passed. From dot 1 to dot 2, 1 second has passed. From dot 2 to dot 3, 1 second has passed. So each successive dot, an equal time interval has passed, right? Same thing with this car right here. And from there, we can actually see how the motion relates to speed and velocity, right? So speed measures only how fast an object is traveling. But the average velocity tells us direction and the average speed on an object. So I want to make this very clear. Speed only shows you how fast an object is going, right? Some people really some people have that misconception that velocity and speed are interchangeable. They're the same thing. No, it is not. Velocity consists of speed and direction, and speed is just a way of measurement. Hey, hopefully I'm still recording. Yes, I am. Okay. Sorry about that. So now that we discussed the difference between speed and velocity, you can understand that velocity is a vector, right? Because what did I said here? It's a direction plus the speed. So that's the magnitude, right? But speed isn't because it doesn't have a direction, right? Right. So now, because of that, we have two separate equations to tell us about more of these terms right here. So speed is the distance traveled in the same time interval over that time interval, right? So if I was a runner and I don't know how I was running, but I know I covered maybe 20 meters over a period of 5 seconds, right? So 20 meters over 5 seconds, that is 4 meters per second, right? That would be my speed. However, displacement, so average velocity, displacement over time interval, it's the same thing right here. If I were to take a path, right, from this red dot to yellow dot, my displacement would be 5 meters to be specific. And let's say that I take about 5 seconds to cover this displacement, right? So what does that mean? Well, 5 meters over 5 seconds, that would equate to about 1 meter per second as my average velocity, right? Now I want to make this very clear. Average velocity only tells us the path the particle is undergoing. It doesn't tell us what's going on overall. So what I mean by that is just because I start at red dot, yellow dot at 1 meters per second square as my average velocity doesn't mean that I've been doing that, right? I could very well just travel very fast and then slow at the very last mark, right? Or slow at the very first mark and then thrusted myself towards the very end, right? There's many ways that you can interpret, excuse me, there's many ways you can interpret how the particle is moving from this red dot to this yellow dot if and only if you're given the average velocity, right? You really don't know how the object is traveling based on speed and stuff. Therefore, average velocity and velocity can only equal if and only if the object is traveling at constant speed. So, what do I mean by that? Well, again, going back to that red dot and yellow dot situation, you can see here that what we established is my average velocity was 1 meters per second, right? Now, let's say that I've been previously, like before I approached this red dot, like let's say I was right over here, I have been constantly running at 1 meters per second for a long time, right? So we can take into account that I've been as a runner ran 1 meters per second for a very long time, right? And when I approach this red dot, and again, we already announced that our average velocity is 1 meters per second, right? That means that our velocity has to be 1 meters per second, right? Because what I said previously, the idea that velocity that I've been traveling at 1 meters per second constantly, right? I'm not changing that magnitude nor direction. It's still constant, right? It's not changing, and um, that's why the average velocity equals to the velocity. It's like saying that if a car was to travel at constant velocity for a very long time, and then someone were to ask you, what's its average velocity? Well, it doesn't matter because it's going to cover the same displacement over the same time interval, right? Well, not the same displacement over the same time interval, but the same ratio, right? If the car covers 50 meters over 10 seconds, that's 5 meters per second, right? The car covers 100 meters over 10 seconds, that will be 10 meters per second. Wait, no, No, I did that wrong. Sorry. Scratch that out of your head. But it's basically the idea that you know the average velocity equals to the velocity because no matter how much you travel over a period of time, it's going to equal to the velocity. That makes sense. Okay. So then we will move on to position versus time graph, where we basically see the position of the object from this little diagram right here. You can see that the green arrow shows what the object's doing. And from there, we actually graph the position on this position versus time graph, right? So time would be in minutes in this case, and it's on the x-axis. Y is position, it's on the y-axis, right? Okay, making sure that I'm recording. I'm sorry about that. But yes, this is the graph that's gonna tell us everything. Well, not everything, but most of the case, the main things that we want to know about, the basic movement of this particle or object. So what we need to know is that the slope of the graph represents velocity, right? And from our formula, velocity is displacement over time, right? So if that's displacement over time, then it's not just x final minus x initial over t final minus t initial, right? That's basically slope. So from that, we can understand that the slope of the graph is the determinant of the velocity. It determines the direction and it tells us how fast it's going, right? So the steeper the slope, the greater the velocity. It's pretty much basically it. So from the right side graph right here, you can see here that we've connected the dots, quite literally from this graph right there. We have connected the dots, and you can see here that there is 3 forms of different, slope lines, right? You have one slope going here, then going here, and going here. So what we can analyze from this is we start at 0, 0, right? We have traveled about 200 meters over 3 minutes, right? Watch the units, which is basically around, let me just do this calculation. So 200 meters over 3 minutes is basically 66 meters over a minute, right? Okay, then what happened here? Well, we traveled less, right? We didn't even like cover 300, maybe even less, like maybe 225 over 3, because that's how long that we've been traveling that speed for, would be about 75. Yeah, wait, no, sorry, wrong. We covered 25 distance, there you go, 25 meters over speed of 3 minutes, right? That would give us the 8.3 miles per minute. So I want to reiterate, this slope is traveling at, right? It's traveling at 66 meters per minute, right? Because we found out that 200 minus 0 over 3 minus 0, right? Okay, now from here to here, we are going at 8.3 meters per minute, right? Because we took, I don't know, maybe this is like 225 minus 200, right? Don't forget the displacement formula, over 6 minus 3, right? Which basically gets you to around 8.3. And finally, from 6 to 9 seconds, we have this jolt of a velocity where we're traveling at, let me see here, 500 minus around 225, right? 225, that's displacement, over a time interval that we've been traveling, which is basically for 3 seconds. That would equate to 91 meters per minute, right? So, from what we can discuss is that we can find the velocity for each segment of the graph using displacement over time, right? And follow through that formula. Don't make it more complicated than it has to be. So from there, we can actually graph this on our velocity versus time graph. Now, velocity versus time graph, again, it's just I'm going to try to make it a smooth transition towards position versus time, so bear with me. So we have found our slopes, right? This is going to be 67 miles per minute. This is going to be 8.3 meters per minute. This is going to be what I have written, 92 meters per minute, right? So from there, you can see here that it can be notated on a velocity versus time graph as just constant lines, right? You can see here that what this basically tells us is that it's that action right here, right? We've been traveling for about, and they got it to like 1 meters per second, but I'm just gonna assume that they are converting it correctly. So they are traveling at 1 meters per second throughout this 3 seconds, right? And what does the velocity graph shows us? The velocity graph shows us that this thing has been moving at 1 meter per second, right? It's not changing, right? It's not changing speed, right? Or velocity for about 3 seconds, right? So that's the first segment. Now the second segment is the same thing, right? We found out that the second segment is 8 meters per minute, right? So they translate that to less than 0.5 meters per second, right? But you can see here that it doesn't matter whether the conversion is wrong or not. It's the idea that they got this horizontal unchanged constant velocity, right? For a duration of 3 seconds, which matches our segment right here. But what about this one? What about the top one? Same thing, right? We found the speed and the direction. So we found the velocity. We can plot it on this velocity versus time graph, right? And we found out that it's more than half, or more than 1.5 meters per second. And that thing has been traveling at that velocity for about 3 more seconds, right? And you can see here that what I basically did is, after I find the slope of the x position versus time graph, what I would then do is graph a velocity versus time graph and make that slopes, like make these lines into just straight lines, right? Because it doesn't make sense to say that the velocity is, a slope, because what that basically tells us is that the velocity is constantly changing, which doesn't make sense here, right? We know, well, the only point that it changes right here and here, but even then, those points are what we call instantaneous point. It's basically this like dotted like line right here. But even so, you can see here that this is a clear straight slope, right? There's no curvature, there's no deviation, there's no like weird shapes. It's just a straight line. That indicates that velocity, right, on the velocity versus time graph, the velocity is written as a constant line because there is a slope on the position versus time graph, right? Now, let's say you did encounter it, right? You did encounter a slope like this where you can see there is a curve in the x position, xy graph, right? Or xt graph. Now, I want you to conceptually think to this. If we have a strong microscope, we can actually zoom into the graph until it gets very, very straight, right? You can see here that that's what happens. And look at the time, 0.2 seconds. That's not even 1 second. That's like a very, very small time has passed, right? And that's one of the ways that you can do. So you can just zoom in and then find a very, 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 very accurate guess by using the average velocity, right? It'll be off slightly, but it's good enough to say that that is the instantaneous velocity. If that makes sense. Like for example, 1.6 over 0.2, that's like 8 meters per second, right? Well, yes, we did use the average velocity. What we did here was we actually increased our field of view by just zooming in and then take the line when the line is straight. That's what we basically do to find instantaneous velocity on a graph. But obviously we don't have that powerful microscope, so there are other ways you can find it, right? We'll be discussing that in kinematics, but for now, we move on to velocity to position, right? So I've told you how we can get from position to velocity. The same process applies to velocity to position. what we have here is that we have the constant line that is not changing, right? So velocity isn't changing. So in this case, we are traveling at 1.0 meters per second for 15 seconds. So what does that tell us? What does that tell us about the slope on the position versus time graph? That basically tells us the slope from 0 seconds to 15 seconds, that the velocity, or that the slope of the x graph is 1 meter per second, right? It makes sense, right? We basically been traveling this velocity for duration of 15 seconds, right? Well, what about this velocity right here? Well, same thing right here, right? We have traveled negative 3.0 um, speed for about 5 seconds, right? So it tells us the direction and the magnitude and the duration, right? So let's put that together. My slope is traveling negative the direction at negative 3.0 meters per second, right? That is my direction and magnitude. And how long? Well, 5 seconds, right? From 15 to 20. There you go. That is basically it. Now, we move on to a very important concept that I think he might gloss over, is that area is displacement on the velocity versus time graph. So what do I mean by that? Well, you can see here that this is a velocity versus time graph right here. I just crossed out the notation because this was, it belonged to another graph, but it doesn't defeat the purpose of what I'm trying to explain. So what we have here is a thing that travels 2 meters per second as constant velocity, then 0, then negative 2. So what we have is that these areas under the curve. Now, what I mean by that is under the solid black line that is notated, right? So under here and under here, which the black line is right here, right? This is basically displacement. Yes, you heard me right. This is displacement. Okay. Now, how do you analyze that? Well, there's numerous ways you can analyze this. So if I were to ask you what's the displacement from 0 to 2 seconds, you would have to find the area from 0 to 2 seconds. So it would be 2 times 2, which is basically 4 meters, right? And same thing here. From 4 to 6, right? Again, notice how I said 4 to 6. You're not starting at 0 to 6. You're starting at 4 to 6. 4 to 6, you have travel for 2 seconds at a negative 2 velocity, 2 meters per second velocity, right? So 2 times negative 2, it's negative 4. So this is 4 meters if we're doing 0 to 2. This is negative 4. This is negative 4 when we focus on 4 to 6, right? But now what happens when I tell you to analyze the displacement from 0 to 6? Well, now you have to add these two together, right? And be mindful, and here's the thing, be mindful of the signs of the displacements, right? If the displacement is under the 0, right, then it is a negative displacement. And if it's above 0, it's a positive displacement. So you add displacement, in this case, that will equate to 0. So if I were to ask you what is displacement from 0 to 6, it's 0, pretty much, right? So we're now going to move on to practice problems, which is going to be in the next video. So hope you guys actually, understand a little bit more about these concepts, and I promise that you'll see that when I'm doing these practice problems, I will be using these terms to guide me to the right answers. But for now, all I want you guys to do is get familiarize yourself with these kind of concepts. That's pretty much it.